of Universidad 3 de Febrero in Argentina. As a pianist, he specializes in contemporary music and has given world and Latin American premieres of pieces by Steve Reich, Christian Wolff, Walter Zimmermann, Peter Ablinger, among others. He has conducted multisensorial performances involving music, dance, visuals, taste, and smell in Argentina, Finland, and France. So we welcome Bruno Mesz.
Thank you very much, and thanks to the organizers for having me. I apologize that I'm going to consult my notes to keep things flowing because of my English. So I'm going to talk about the evolution of tango harmony in this period of classic tango from the 1910 to the 1960s. And tango is for sure the most transcendent in the sense of internationally known collective cultural creation of the Rio de la Plata region, which is basically two countries, Argentina and Uruguay. And I'm reasonably sure that you know these guys, or at least their most famous tangos, Carlos Gardel on the left from Argentina. So the tangos, for instance, Por una cabeza, y Buenos Aires querida, although he was mainly a singer, but also composed some famous tangos. And on the right side, for Uruguay, you have, for instance, Gerardo Matos Rodriguez, the author of La Comparsita. And by the way, the motivation of this study of tango history was because my colleague Pablo Amster and me were invited to play La Comparsita in the piano of the composer in Montevideo, because it is the centenary of the tango, and also to give a talk on tango and mathematics. So we decided to take a look on the evolution of tango. So although there are several books on tango history, there are, to the extent that we know, there are no computational studies or quantitative studies of tango history. So recently, due to the availability of big corpora of musical data, they have appeared many quantitative evolutionary studies of music. And recently also complex network methods have been employed to study musical evolution. So we want to look to tango from the complex networks perspective. We were inspired by this paper by Serra and others, who looked at the evolution of popular music from the 50s to now, to the actuality. But they had access to a big corpus of 1 million, maybe you know it, the 1 million songs corpus. So we are able to assemble a much more modest corpus of 510 tangos, which we downloaded from this site. So we have this distribution of number of tangos per decade, and note for the older tangos we have a few, just 16 that we could get. So how we turn tangos to a network? So what we do is the same thing as in the paper by Serra. We extract from the audio signal the chromogram frame by frame. So we keep only those frequencies in the chromogram with sufficient energy, which means an energy above the average over all tangos. So we have a sequence of chroma pitch classes, and these are going to be the nodes of our network. Those are the nodes, and the links represent the harmonic transitions between these, we call them code words, these sequences of chroma pitch classes. Specifically, for the purpose of studying the evolution of harmonic discourse, we've formed 5 collections of code words, one for each decade. So 2 code words like this are connected by a directed edge if they appear in consecutive analysis frames. But we avoid self-connections of one code word to itself. So in this way, we have 5 networks, one for each decade. So the problem with this is that many of the code words are not what you would analyze as harmony in Tango because of noisy frames. They even appear like the 12 tone clusters or many dissonances. So we consider 2 kinds of networks. In one type of networks, we have these code words, the whole code words, but the other kind of networks we considered, we filtered the chords and just take the triadic chords, which with at most 4 pitch classes, including singletones and diads, but triadic. So once we have the networks, we want to look, as is usual, to the distribution of the frequency of the nodes. And we are able to fit 2 different kinds of models, one for the unfiltered networks, which comprise all code words, and a different one to the triadic networks. So the first one on the left is quite well known, is the Zipf's law, which is common in linguistics. When we have that the number of occurrences of the chord of rank R, that means rank 1 means the most frequent code word, rank 2 the following, and so on. So the number of the occurrences of the word of the chord of rank R is like a power, a negative power of R, 1 over R2 up power Z. And for the triadic networks, I will explain why we couldn't fit Zipf's law, but a modified power law, which is that model in the right. So the models are beyond the quantitative aspects are derivable from some simple hypotheses, which are easy to understand if you are talking of a single piece of music. But here, remember that we have networks of the whole harmonic skeleton of the tangos of whole decades. For a single musical piece, it's easy to derive the models. For instance, Zipf's law follows from the assumption that as you add more and more chords to a given piece, you create a context, and then this context favors the reappearances of the chords that already have appeared and inhibits, in a way, the appearance of new harmonic structures. So if you assume that all chords appear proportionally to their frequency, the frequency of the previous occurrences, and the new chords are added at a constant rate, you can derive a Zipf's model. But this is valid for in the long term for large ranks. So in the case of the unfiltered network, we have over 4,000 different chords. But if you only consider triadic chords, you have like 100, exactly you have 151 possibilities. So you never reach a long rank. So this other model, the model 2, it can derive from an assumption, a refined assumption as how the innovation occurs in a piece. So you don't assume that the new chords appear at a constant rate, but that the rate decreases over time. And if you have the assumption of that the number of different chords is like the length of the piece to a power nu, you can derive the second model and look see also that the model has a couple of coefficients A and B that you can manipulate to adjust to the data. So using this model, we could fit the triadic distribution of frequencies in the right. So this is easy to understand for a single musical piece, which is more strange is that we are looking like hypertext or hyper pieces from the whole decade. So maybe we can think of this process, underlying process of generating the networks, like tradition and influences between composers, producing these processes of innovation, inhibition of the rate of innovation. But in any case, whatever, if this process is at work or no, a small power nu or large Z in the models means a more compact vocabulary of chords. So a few chords are important and dominating, and the others appear much less frequently. So we can compare with what happens with these exponents with other corpus like the 1 million song, and we get these numbers rather constant over time in this small interval for the unfiltered networks, and these are larger than the number for that Serra and others get for the 1 million song corpus. So we have here a more compact vocabulary, and if you accept that this is due to an innovation process, maybe less innovation. Of course, the time period is different. This is from the 1910 to the 1960, and there is from the 50s to now, and also we are looking just at one genre, tango. For the model, second model, we got a much wider range and still less rate of innovation, still more compact vocabulary, and it's different from decade to decade. So we have this from 2.48 to 6.05, so it's different, varies in time. We can look also at chord types. Could you see I think you see the types like the diminished triad. And their rates, the percentage of the chords over all the chords is more or less constant over time. So it varies very little, but if you look at the augmented triad, it doubles its rate a long time. It increases. It's still not very frequent, but it tends to increase. And also I think the minor 7, the minor 7th. Yes, like increase like a factor of 2. So in a sense, the vocabulary is getting more sophisticated for these kinds of chords. Also, natural thing is to look at the modes, minor versus major, and you see this thing. But remember that for the first decade we have few tangos. So if we look from the 20s on, this is the ratio between minor tangos versus major tangos. It's always greater than 1, but it tends to increase to a factor of 2. So maybe when Borges said that tango tended to get more, ¿cómo se dice? Sombrío, shadowy, or somber a long time. Well, here's like a quantitative correlate. Other network coefficients that are worthwhile to look at are the number of connections between the nodes compared to the all possible connections. These are measures of density or sparseness. So on the left you have a dense graph, and on the right you have a sparse graph. And of course, it's natural that in music you have sparseness of graphs because not all chord transitions are common or allowed. And also for learning style, through statistical learning, you need like this sort of connectivity. No? You don't have to learn so much chord transitions. So, for instance, for triadic chord words, we have around 2,000 transitions for all decades, which is reasonable to learn. Other common network coefficients are the degrees. So this is an example. The central node on the left has degree 5. That means that it's connected to 5 other nodes of chords or chord words in our case. And on the right you have degree 2 node. So we can again fit the degrees distribution by Zipf's law in the case of unfiltered networks, and by the other model which is due to Damien Sanet for the triadic networks. But there's a difference. For the triadic networks, you can see that the median of the degrees tends to increase a lot in time. So this means that there are richer connections, that from one chord you can go to many other different chords. So this is a sign of an enrichment of harmony. This is maybe explained by this, by a strong tendency to greater freedom of harmonic discourse. So these are some curious facts. When you compare the frequencies to the degrees, they are almost in a perfect monotonic correspondence. So the most frequent chords are also the most connected chords. Also, this is strange. The out degree and the in degree. Out degree is how many chords a given chord can lead to, and in degree is from how many chords it can come. Are almost the same for the all major and minor triads. So there's a symmetry there that is not present in classical music, but it has been found in the 1 million song, for instance. So So two other measures of harmonic discourse is how the chords cluster. So you measure considering triplets of chords. So and how many closed triangles, like in the right, you can form between triads. That's what that's mean is that we can get, for instance, from the bottom yellow note to the top yellow note in the right, in two different ways, like directly and going to the third note, yellow note in the right. So there are more clustering, means more of these closed triangles, and means so much more different ways to reach from a chord to another chord. So more clustering is also a measure of a richer harmonic discourse. So we, in fact, found this more clustering in time. For having any sense of this clustering measures, you have to compare with random networks, and you see the triangles are the real networks, and the squares are the random networks. So you have C as the clustering. So you have much more clustering for the real tango networks, but also in time. Look at the blue triangle is the decade of the 10s, and the other are from the 20s to the 50s, and they are more to the right, no? More clustered. And also the shortest path length, how many chords you have to transit for going to a chord to another, tends to decrease. So the way from one chord to another is shorter across time. And that means probably that the transitions are more bold, more original as time goes by in tango, which is exactly the opposite that Serra observed in the 1 million song corpus. And I think I don't have much time, but I just wanted to say that we have to look also at individual tango networks, because you could not overlook the importance of a single tango. You can compare tangos from different decades, single tangos, and see if they can be distinguished by the topology of the harmonic networks. And in fact, using some quite recent methods due to Freiman, we observed exactly this, that you can distinguish decades of tangos by the topology of individual pieces. So, okay, thanks a lot. For the what?
How did you define chord for the clustering and for the degree analysis? Are they sets of intervals, or are they
Sets of chroma pitches, all from 0 to 11. Yes, I forgot to say, we transpose all the tangos to C to compare. Yes. Well, we use an algorithm based on Krumm-Hansel tone profiles, which is in a toolbox for MATLAB. No, but you can account for modulations relative to the C key.
so much
Yes. The sound files were almost all contemporary to the year of composition. So there's not a time difference, except in a few cases. Well,
We'll present Christofer White, who received his PhD from Yale and has also attended Queens College at the City University of New York and Oberlin College Conservatory of Music. His articles have appeared in Music Perception and in Mathematics and Computation in Music, and he has presented papers at national meetings of the Society for Music Theory, as well as several regional conferences. His research investigates algorithmic and linguistic theories of music by presenting computational models of musical style, function, meter, and communication. Christofer's research has also focused on geometrically modeling early 20th century music, especially the music of Scriabin and Alban Berg. Today he will talk about cross-entropy as a measure of coherence and uniqueness. So we welcome.
Thanks, and I'm so glad that I get to follow that paper because it lays out a bunch of things that I'll also talk about. So today I'm going to talk about how we can use the concept of cross-entropy to quantify some similarities and differences between groupings of pieces. And so I'll be able to ask questions like, how similar is Mozart to Beethoven? Or how typical of the 19th century is Brahms's style? Like, how likely is Brahms to have been generated by the 19th century? And I'm going to use the concept of cross-entropy, which is based on entropy. And if you know one thing from information theory, it's entropy. So what entropy does is reflects the complexity of a signal, right? And if we go from right to left up there, you've got the log probability of some observation O that is then weighted by the probability of that observation to occur in the stream. So you've got the log probability that then is weighted by how often it occurs in the stream, the probability of O. And then you do that for all instances of O in some observation stream. And so what you'll get is a entropy of 0 for an observation stream generated by a one-sided die. If it's like if there's no complexity whatsoever, you get an entropy of 0. If you have a two-sided die, you would have an entropy of 1 if you use a log base 2. And then you get an entropy of infinity if you have a die with infinite sides, because it's infinitely complex, right? And so what entropy is going to show us is how well a model can predict itself, because an infinitely complex model can't predict itself, and a one-sided die can optimally predict itself. What cross-entropy does is it brings a model in that is different than the observation stream. So now, instead of having on the far right-hand side just the probability of, the log probability of O, you've got the log of a model's prediction of O. So the probability of a model's prediction of O. And so it reflects how well a signal O is predicted by M. And this measures like the perplexity of a model looking at an observation stream. So high numbers will occur when the model doesn't predict the observations well. And low numbers will occur when the model fits the observation well. So let's go back to our die here. If you use a three-sided die to predict the roles of a two-sided die, that's going to return a higher cross-entropy than if you use a two-sided die model to predict a two-sided dice roll. But it's going to be lower than a four-sided die model because a four-sided die will be worse when predicting a two-sided die than a three-sided die. And then when the models match exactly, it's going to be equal to the entropy. So my argument is that given some large collection of pieces or corpus with potential smaller divisions or subcorpora, if a subcorpus predicts itself well, that is, it has a lower cross entropy than does any other subcorpus in that corpus, that subcorpus is unique. And if that subcorpus predicts itself better than does the overall corpus, that subcorpus is going to be coherent. And I'll come back and formalize this in a second. But first, let me lay out my materials here. So what do I need? Well, I need a corpus. And I'm going to need a way to divide that corpus into subcorpora using some parameters. So like associations with composers or dates. So I'll have to have some way to group my big corpus into like composers or into chronological groupings. And I'll need some probabilistic model to measure these subcorpora. So the corpus that I use is the Yale Classical Archives corpus. The YCAC are a bunch of MIDI files, which are drawn from classicalarchives.com. I, in this study, use just the composers that have the most pieces associated with them, and it's the usual suspects that you would expect. Bach, Beethoven, Brahms, et cetera, people that you'd run into in your typical music history book. The average corpus contained 231 pieces, Wagner being the smallest with 33 and Scarlatti being the largest with 554. You know, I mean, Wagner's also got really long pieces too, so. They're also tonally analyzed in this corpus by window, so you get modulations. And the verticalities are divided into unordered sets of mod 12 scale degrees, which is basically Roman numerals without inversions. So like you'll say, this slice is a 5-chord, or like so, ti, re, fa, but it won't tell you whether so, ti, re, or fa are in the bass. So you don't know whether it's a 5-7, a 5-4-3, a 5-6-5 chord. But you know what scale degrees are in every moment. So now, what probabilistic model do I use? I use a trigram model, which I chose trigrams because it balanced complexity, precision, and tractability. When I used bigrams, it just didn't seem precise enough. When I used 4grams, it began to get intractable. And so these are Markov chains where your n equals 2, but it asks the probabilistic question: how likely is this chord given the previous 2? So if you were to divide this up into trigrams, you'd get divisions like that, and the question would be, I'm going to use the piano. So if you have those first 2 chords, the trigram question is how likely, given those first 2 chords, is that next chord to happen? So how likely is there to be a C7, a dominant 7th chord, given the 1 chord and the 4 chord that precede it? Wait. So uniqueness. I thought that I would bring in an analogy which, given that I'm traveling internationally, that showed my Americanness. So the intuition behind uniqueness is a statement like, I can tell that this hamburger was made at the McDonald's on East Main Street. That hamburger is unique to that particular McDonald's. And the claim there is that there's something about this particular hamburger that makes me sure that it was generated by a particular McDonald's and not any other McDonald's. So that hamburger is unique to that McDonald's. So in terms of cross entropy and subcorpora, a subcorpus is unique if the average cross entropy for each piece in that subcorpus is lower when the pieces are judged by its own probabilistic model, by the probabilistic model that comes from that subcorpus, than by any other subcorpus in the larger corpus. And the comparisons are going to be subject to windows of statistical significance. So let's formalize this with a little bit of pseudocode here. So for a subcorpus in a corpus, for each potential division of a larger corpus, take each piece for each piece in the subcorpus. You take each piece out. So let's imagine that we've got the bigger corpus and we're taking out the Mozart subcorpus. We would take each piece from Mozart each piece by Mozart out of that subcorpus. And we create a model M that returns the probabilities of the trigram in that subcorpus minus that piece. So we take the piece out of the Mozart subcorpus and we create a probabilistic model from the rest of those pieces. From that piece that we've taken out, we're going to create a succession O, an observation stream. And then we will judge how likely that piece was to be generated given the remaining pieces in that subcorpus. So how likely were the rest of Mozart's pieces to generate that single piece by Mozart? And we will do that for every piece. So we'll put that piece back in, we'll take the next piece out, judge its probability, put that piece back in, take the next piece out, and so on and so on and so on for all of the pieces. And we will make a list H for each of those cross entropies. Then we will go to each other subcorpus in the corpus. And we will make a new model that returns the probabilities of the trigrams in each other subcorpus. So we've just done our Mozart subcorpus. We would then take, let's say, the Mendelssohn subcorpus and say, how likely are each of Mendelssohn's trigrams to occur? And then for each piece in that original subcorpus, we'll create the O again, the chord successions, and we will say how likely are those chord successions to occur given that other corpus. So we take each Mozart piece out again, and we say, hey, how likely are you, Mozart piece, to be generated by the Mendelssohn model? And then we take the next Mozart piece and how likely are you to be created by that Mendelssohn model? We go all the way through. And then we do that for all other subcorpora. And we say, so how likely are all Mozart's pieces to be generated by the Bach model, by the Brahms model, by the Schumann model? And we create a list for each other composer. And then, if the mean of the list of that other composer, minus this standard error to create our significance window, is greater than the mean of our original composer, plus its standard error, then the corpus is unique. So if the Mozart list is lower than any other list that we created, Mozart's model is unique. So this is how it would look. So if a composer that is observing itself creates a lower cross entropy within a statistical significance window than any other composer, it's going to be unique. Coherence works the same way, but the claim now is the East Main Street McDonald's makes hamburgers consistently different than McDonald's does in general. The claim here is that the output of a particular McDonald's is better described by what happens under that roof than by the franchise as a whole. And in terms of our subcorpora, a subcorpus is coherent if the average cross entropy for each piece in that subcorpus is lower when the pieces are judged by its own subcorpus than by the corpus as a whole. And again, subject to a significance window. So our pseudocode is going to look the same, except that instead of taking the individual Mozart pieces out and saying how likely are you to be generated by Mendelssohn, by Bach, by Brahms, it says how likely are you to be generated by the corpus as a whole. And so then what we're going to compare is whether the Mozart model judging Mozart's pieces creates a lower cross entropy than does the Mozart pieces when judged by the overall corpus. And if that's true, then it's coherent. And so this is what the bars would look like if a composer judging itself is lower than the cross entropy judged by the whole corpus. It's coherent. So now let's use it and see how this works. Let's group the larger corpus in different ways. Let's do it by identity, by composer, but let's also do it by chronology. I do it by 30-year epochs, by 50-year epochs. And then I use some machine-learned clusterings to also divide up my corpus. So first, let's talk about identity. 74% of composer-by-composer comparisons were significantly unique, and 88% were coherent. So let's look at an example that worked really, really well. And remember, the lower the cross entropy, the better the fit. The higher the cross entropy, the worse the fit. So I'm going to show you a graph where the cross entropy is going to be on the left. We're going to start with Handel's subcorpus, judged by himself, and then judged by everybody else. So there's everybody else. So Handel judging himself returns something around like 4.6 For cross entropy, I'm using log base 2 here to do it in bits. And then it is in fact coherent because that is lower, significantly lower than when the overall corpus judges Handel's subcorpus. And it is significantly lower than everyone else too. So Handel is unique and coherent. This is an example which is more or less average. So Mendelssohn judging himself, you get something like 5.7, 5.6. And it is significantly better than when Saint-Saëns judges the Mendelssohn corpus, but not when Schumann judges that corpus. The model cannot, this probabilistic model cannot tell the difference between Mendelssohn's model and the Schumann model. And that goes for a couple others. Brahms, Chopin, Handel, these all are indistinguishable in the way that I frame this from the Mendelssohn model. The 50-year corpora. So it performed worse than composer comparisons. 68% were unique, 82% were coherent. And a lot of this stems from the fact that one 50-year period, 1751 to 1800, did not have a single successful comparison. Let's talk about that. That happens right here. So this is 1751 comparing to itself. It is higher than any other cross entropy judging it. In fact, notice that the bars around it, so 1701 and 1801, actually judge those pieces better than it judges itself. And I'll talk about that a little bit more when I go into my large-scale analysis at the end. But that's kind of interesting. That 1751 to 1800 just doesn't predict itself very well at all. Most non-unique findings were the result of comparing chronologically adjacent epochs. So if we look at 1801 to 1850, this is more successful, more typical. It gets a non-unique comparison when you go to the next half century. So the next half century is statistically indistinguishable from 1801 to 1850. The previous half centuries provide a pretty good, pretty distinct models though. So I end with, my last groupings are machine-learned subcorpora. This comes from some work I did a couple of years ago where I clustered composers based on how frequently they use these 3 chord progressions. I used the k-means clustering where I found that 7 and 10 groupings turned out to be optimal. So in my 7 groupings, you get a couple of individual composers like Bach, Bird, Debussy, Scarlatti going off by themselves, but you get clusters like the Viennese composers tend to group all together. The Romantic-y composers tend to go together. The Baroque composers tend to go together. And these groupings perform excellent. K equals 7 provides nearly perfect results. Debussy is the only one that doesn't do a good job. And it's probably because he has such a small corpus, but it's also probably because Debussy is, a wacko. 10 clusters is a little bit worse, but if you discount the 2 smallest corpora, Wagner and Debussy, it also performs extremely well. But we shouldn't be surprised at this, given that we're grouping subcorpora by 3 chord progressions, and then we're testing them using 3 chord progressions. So there's a similarity between how we're grouping them and then how we're testing them. So this grouping, it makes sense that this would work so well. Here's how one would look. So this is the romantic-ish composers judged by everybody else, and they are significantly lower than the other models. So what can we do with this? Well, we can describe stylistic trends in compositional schools. Some composers seem to be non-unique in of themselves when defined by their surface trigrams. But then when you group them together, they do create unique groups. So like Brahms and Schumann are a good example. That when taken apart, they don't create unique models, but when you put them together, their models do distinguish, that model does distinguish itself from the remainder of the larger corpus. We can also look at moments of innovation. So non-coherent moments show years when too much is happening for that subcorpus to predict itself well, like the early 19th century, or the later 19th century, and by that I mean 18th century. It's predicted by the statistics of neighboring historical epochs better than the pieces in its own time period. And this is probably because there's a huge amount of change that happens in this half century. So that half century contains the late works of Telemann and Scarlatti, the complete works of Mozart and Haydn, and then ends with the mature works of Beethoven. And that's an enormous swath of styles. And so you can imagine why the earlier models predict it better and the later models predict it better than it predicts itself, because there's just so much going on inside that model that it just is not coherent. We can also talk about authorship using these models. We can say, hey, was a piece authored by this group of composers? So I do this test on Vivaldi's, quote, opus 13, unquote. It's in quotes because Vivaldi only wrote 12 opera. Vivaldi's opus 13 is a group of musette concertos. The musette is a French bagpipe. It was published in Paris. And then it turned out, after a criminal investigation, that these were published by the musette virtuoso Nicolas de Chedeville. And if we compare this opus 13 to the K equals 12 divisions, it actually turns out that, that the Telemann-Vivaldi cluster predicts these pretty well, but also Handel. So he could have passed them off, I mean, at least in terms of this model, as Handel's pieces also. And so we can sort of have a conversation about authorship given this kind of testing. Some ideas for future work. Right now, there's relatively few composers that I'm working with. I could expand the number of composers under consideration. Composers don't compose, and we don't really hear using surface trigrams, right? So I could consider reproducing these models with, let's say, a generative probabilistic grammar, something like that, something that's a little bit closer to actually how we hear music or how music is composed. And I could introduce things like melodic figuration, recurrent basslines, orchestration, ornamentation, yada, 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 because right now I'm just looking like at these verticalities moving to one another. And I'm also limiting myself to a particular repertoire of common practice Western European art music, and it would be interesting to go outside of this sort of canonical repertoire and see how this would work outside of that. So thanks so much. I wrote, the code is written in Python. Python. And then some of the statistical analysis is done in R. Yeah.
So if you want to increase your number of cooperatives, when your creator becomes too large and it takes a lot of time.
Some of this, one issue about that constrains my my study is, especially using R, like R starts to shake and complain when your data set gets too large. Yeah, and so that is a thing that I struggle with. But I mean, I just have to look for new tools, better tools to expand my data set. Yeah. I mean, that's a super crucial question about what I mean by tonal analysis. We do a windowed key profile analysis, just like the last speaker. We use the Bellman-Budge weightings for the key profile analysis. And what we do is we move it through, I believe we take a 4-measure window, and we move it through, and if we I can't remember what our threshold was, but if the correlation coefficient to the key profile goes below a certain threshold, we call it ambiguous and don't use it. All right? So what we're actually looking at here is tonally analyzed music that is certainly in some key, at least when we judge it by the key profile analysis. Yeah, I know. I'd love to chat about how that would look. That's why I did 50-year models and 30-year models. I also piloted some 10-year models, but I didn't get 10-year chunks. I mean, by continuous, you mean like a moving window? Yeah. That's a great idea, and I should do it. Yes, that's my answer to that. Yeah.
For the future, would you consider Palestrina, Victoria, Lassus, and Cristobal de Morales?
Absolutely. I think that I don't have that data set, that data set's available, but I just started using with this data set, and I think that would be so interesting. I think we might have to change the way that the sets are represented. Although it might just work wholesale from this, but it might also be the interval structure between voices or something like that, because they're compositional. That might better represent the compositional style of that era. But yes, that would be really interesting as well. Yeah. I'm not applying spell check. It's this one. I knew somebody would ask this question. I do it actually with three different divisions. The salami slice is every time a note is added or subtracted from a texture. The beat method, I take the beat metadata from the MIDI files, which is like fine, but not great, and I divide it by each beat. And then I take the subdivisions of those beats, which is also in the MIDI metadata. And then I throw them all together in a big pot and assume that things which are most recurrent will bubble up to the top. That's what I'm using in this. I mean, I think that this is a very, I want it to be as theoretically naive at the outset for something like this, and so I didn't want to define what a chord was in any more theoretical way than, hey, what's going on immediately on the surface. And I think that it would be an interesting way to take a next step by doing something like what Bruno was talking about, where you've got his triad method. As opposed to just taking the raw surface statistics. Oh. Yeah, that's. Yeah, there's a couple of interesting dimensions to that question. First off, doing a composer throughout time is a thing that I should certainly do, and see whether, like early Beethoven clusters with Haydn more, and then late Beethoven clusters with Schubert, let's say. That would be cool. But in terms of popularity, you'd have to figure out how to determine that. I've seen. Just playing with data, that early composers tend to have smaller entropy than their juvenile works tend to have be predicted easier than their later works, which is what you would expect. And in fact, there's sometimes a curve where their later works tend to be a little more conformative, I guess. Yeah, right. But it would be interesting to be able to define popularity in some way and play around with that question. Yeah, so we need some sort of again, we need some sort of quantifiable way to relate those things to that in some way. One thing that I've done in the past is show that the cross entropy between two composers is correlated to date, and so you would imagine that, which sort of conforms to that, like things which are historically similar tend to be similar stylistically, right? But it would be interesting to find some sort of metric for like listener-based similarity. Yeah. Thanks, everybody.
I'm so sorry, but so much coffee, we got late. Brian Rodriguez is from Cali, Colombia, the world capital of salsa music. And during his studies, he got interested in the relation between music and computer science. And as he started learning about computer music and natural language processing, he became engaged in a project called Salsa Dataset, led by the Universidad del Valle and other universities from Cali, Colombia. And he began to also study music theory. So he carried out his final project in the computer music field, and that work was the starting point for his presentation today, which is using probabilistic parsers to support composition in salsa music. So here we have Brian.
¿Y hablo? ¿Sí? ¿Listo? Okay. Do you listen to me? Okay. Hello. My name is Brian Rodriguez, and this work is called